we ended last time talking about polar graphs. Without a whole, this is 9.2. Without a whole bunch of terminology and rigor, sort of there's three types of graphs that you're going to run into commonly when you graph in polar. There's the r equals a cos thetas, or r equals a sine thetas. And these guys are circles. They look like, depending on whether it's sine or cosine, we graphed one that looked like this. Right? Cosine's always going to have a diameter on the x-axis, and sine's always going to have a diameter on the y-axis. So if you see this format where it's just a number times cosine or a number times sine, you know you're going to be getting a circle. Recognizing that allows you to graph less points, right? If you don't know what shape you're expecting, you're going to have to plot a lot more points. But if you do know the shape you expect, you can do a little less work. The other one, the next shape, which are either cardioids or limacons, look like a plus b cos theta, or a plus b sine theta. And these guys end up looking, depends on what A and B are, but here's an example like this. It's possible. Sometimes you can have a loop in there. Something like this guy where you loop around it. But it's going to be some kind of heart shape. Okay, whether you have a loop or not depends on how big these are, but if you plot points, you'll see pretty quickly whether you have a loop. And then the last one, r equals sine or cosine of some number times theta with an a out front. And r equals a times sine times some number times theta. So these, when you have multiple angles inside, these guys end up being loops. The number of petals depends on the number you see in front of the theta. If the number is odd, that tells you the number of petals automatically. So if, like, you're graphing sine 3 theta, you'll have 3 petals. Cos 3 theta, you'll have 3 petals. If the number is even, then you have to multiply it by 2 to get the number of petals. So you have to do, you multiply n by 2, so 2n equals the number of petals. So I did quickly on, and I gave you pictures of all these, I think, up above. And then it has all the gory detail, which we don't really care about. Really, if you have a plus or a minus in front, that's going to tell you to expect one of these shapes. If you have a number in front of the theta, that's going to tell you to expect a rose. That's it. That's all you really need to know. But I wanted to plot a couple more, just to give you an idea of how polar graphing works. So let's do it. Let's graph r equals 1 minus 2 cos theta. Now, we're not going into this, we're not getting super hardcore in polar graphs, all we're really doing is plotting points. Now, I always start with my sort of easiest points to plot, which are 0, pi over 2, pi, 3 pi over 2, and 2 pi. If this doesn't give me enough information, then I'll fill in with some extra points. But let's start with this and see what we get. When you plug 0 in for theta, what should you get?
1.
What's cosine of 0? 1. What's 1 minus 2 times 1? Negative 1, right? So cosine of 0 is 1, but then when you actually calculate it out, you get negative 1. Let me draw a little unit circle. So 0 landed us over here. These are the interesting points, at least for now. So what happens when you plug in pi over 2? 0 for cosine, but then when you do out all the other calculations, it ends up giving you 1. When you plug in pi, you get negative 1 for cosine.
3.
So after you plug it all in, you get 3. 3 pi over 2, you'll get 1 again, because cosine 0. And then 2 pi, you'll get
Negative 1.
Often you can see if I have enough information. I'll get more points. So I have a bunch of 1s, which means I have a bunch of circles of radius 1 that I'm going to have to plot on. And I have a 3. So 0, negative 1 means when I go to an angle of 0, I have a radius of negative 1. So that's going to be angle 0. This is the angle 0 usually. But because the radius is negative 1, what happens? So this guy is 0. But negative radius flips you backward. That makes sense? So that's your first point. Negative 1. Radius is 0 theta. Pi over 2, 1. Go up here. Right, when you're at pi over 2, you have a radius of 1. Pi 3. So when you're at pi, which is in this direction, you go out to a radius of 3. So that would be here. Three pi over 2, you're down at 1. So 3 pi over 2 is this way. Down at 1. And then 2 pi, you're back at negative 1. So 2 pi, you end back over here. Any idea what this might look like?
Is it like a rookie part?
So, yeah, you can guess this. Now, how would I know whether it loops in here, like something like that?
There's a point in the middle?
So you either need to do two things. You either need to go and read this table and figure out what the conditions are for A and B to get a loop. Right, this one's a loop. So it says that the first constant has to be less than the second constant in order to get a loop. The first constant has to be less than the second constant. So it looks like we're in this case, which means we're going to have to plot more points right around Which one was this? This was theta equals 0. So let me try something right after and before 0. So what's the point between 0 and pi over 2? Now, I want it to behave nicely in cosine, so give me something that looks nice in cosine. So for example, this is 1, 2, 3, 1, 2, 3, over 2, over 2. Cosine is 1/2 when you're at pi over 3. So when you plug in pi over 3 here, what happens? Cosine of pi over 3 is 1/2. So r is 0. Let's go back here now. Now we have more information. Where does this point go? R is 0. So actually it goes right here. So what's that tell me? That changes my shape. What do you think? See what has to happen now? So the first time we didn't have enough points because we weren't getting a loop that we expected. If you plug in an extra point, then the only way you can make these 2 points work is to put a loop in there.
If you eventually even split it up further, plotting more points, you would eventually plot every single dot in the loop, right?
Right, yeah, absolutely. Like if you're not convinced still, I would go in and plug in 2 pi over 3, 4 pi over 3, 5 pi over 3. Quickly, let's see where these land just to help me get a better picture here. If you plug in 2 pi over 3, is cosine positive or negative?
Negative.
Negative because you're in the second quadrant. So you'll do 1 minus 2 times negative 1/2, which is equal to 2. So at 2 pi over 3, you should be out at a radius of 2. So you're on a circle of radius 2 at the angle 2 pi over 3. Then you can do 4 pi over 3, it would be 1 minus 2 times negative 1/2 again, which would be 2. So when you're over here at 4 pi over 3, you go on a circle of radius 2 again. What do you think happens at 5 pi over 3? What's cosine of 5 pi over 3?
1/2.
Positive 1/2, which makes 1 minus 1, which is 0. So you're at this point again. So if you trace this guy out, he starts here, comes up, loops around, goes back to 0, and then ends. So if you have, like I said, if you have this chart and you know what to expect, then you can plot enough points until you get what shape you expect. If you don't have the chart, then you can just plot 1,000 points and you get the right shape eventually.
What page of the book this chart's in?
It's in 9.2. It's in section 9.2. But I don't know the exact page. Let's do I gave you sine 2 theta, something like that. 4 sine 2 theta. So what are you expecting from this?
Petals?
Petals, rows, right? When you have a number in front of the theta, you're expecting some sort of rows. And depending on whether this is even or odd, you can tell me how many petals. If it's even, you multiply it by 2. So 4 petals. I'm going to start with my usual suspects. Now, you want to be a little careful here. Okay? I want, what would work out really nicely for me is to get pi over 2 after I plug in theta. If you look, when I plug in pi over 2, what do I get inside of the sign? If you put pi over 2 here, you multiply it by 2 and get pi. Right? So to make up for that, I'm going to actually half all of my angles. Otherwise, you're not going to get enough points. Okay, so with these multiple angles, you're going to have to cut everything in half. So instead of going 0, pi over 2, pi, 3 pi over 2, 2 pi, if you cut 0 in half, what do you get? 0. If you cut pi over 2 in half, what do you get? Pi over 4. You just multiply by 1/2. You cut this guy in half, you get pi over 2. 3 pi over 4, pi. So instead of using my axis angles, I'm going to cut all of those in half to make up for this multiplication by 2 and go 0, pi over 4, pi over 2, I'm just copying these. 3 pi over 4, pi. If I wanted to keep going, what do you think I would use? You see the pattern? What are you going up by every time? Pi over 4. So what do you think should come next? Oh, I heard somebody. Yeah. 6 pi over 4, which is 3 pi over 2. 7 pi over 4. This should give you a decent sample to start with. If you don't make up for this 2, you're not going to see the pattern you're expecting to see. If this were a 3 theta, what would you do to your angles? Cut them in a third. So start with your usual suspects and multiply by 1/3. So each time we're multiplying by 1/2. All right, now what do we actually get? When you plug 0 into sine, 2 times 0 is still 0. So sine of 0 is 0. So at 0, we do 4 times 0, which is 0. What about pi over 4? We'll do sine of 2 times pi over 4, right? Which becomes pi over 2 when you reduce. That's the whole point. So 4 times sine of pi over 2, what's that? Just 4, right? Sine of pi over 2 is 1. When you plug in pi over 2, 2 times pi over 2 is pi. Sine of pi is 0. When you plug in 3 pi over 4, 2 times 3 pi over 4 is 3 pi over 2. Sine of 3 pi over 2 is -1. Keep going. Plug in pi, sine of 2 pi is 0. You're seeing the pattern. Plug in 5 pi over 4. 2 times 5 pi over 4 is 5 pi over 2. Where does 5 pi over 2 land? Lands back in the pi over 2, right? 5 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So you're back at 1 for sine. 4 times 1. It's just going to repeat. So what's the next one going to be? 0, and then -4. 0, 4, 0, -4, 0, 4, 0, -4, 0, 4, 0, -4, 0, 4, 0, -4. One, two, three, four, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Everything seems to happen on a circular radius 4 or a circular radius 0, at least for these points. So let me just put a circular radius 4. When theta is 0, r is 0. What's that mean? Where do I put a point? Origin, or pole. Right, whenever r is 0, you get a point right in the middle. When theta is pi over 4, r is 4. So here's the angle pi over 4. When theta is pi over 4, r is pi over 4. I'm sorry, when theta is pi over 4, r is 4. Too many 4s for me to keep track of. So that gives me this guy and this guy. When theta is pi over 2, r is 0. Puts me back at the origin. Now that's only 2 points, but because I'm expecting a rose with 4 petals, that tells me I'm going to look like this.
It looks like it's going to repeat in all 4 quadrants like that.
Exactly. If you move on, 3 pi over 4, -4. You got to be a little careful. Here's 3 pi over 4. Which way is -4 going to go? Down to the 4th quadrant, right? So this is my next point. Then back to r equals 0. Then 5 pi over 4, +4. Back to 0. Seven pi over 4, just down here. -4 though is going to toss me back into the 2nd quadrant. That gives me this guy, and back to 0. All right, so first I go out to pi over 4. Then actually this is my 2nd point. Then I come back out here. Finally.
That is so much fun.
I don't know, I kind of like it. It feeds my brain's need for symmetry. Even though my drawing is not very symmetric. In my brain it looks very symmetric. So, I do polar graphing because it's a decent application of plotting polar points. Okay? And also plugging into sine and cosine. So if you can plug into sine and cosine, and you can plot in polar, you can do graphs. You just have to know what shape you're expecting to get a decent picture.